Okay, so let's see this exercise now. It looks like it's jam-packed with notations. Let's try to understand what the things mean. Z plus, of course, or Z plus, however you want to call it, is the set of positive integers. So that means m is a positive integer. M is some positive integer. Say m may be 1 or 2 or 100, anything. And A is an element in the set Rn from which 0 has been removed. What is Rn? Rn is this set. Rn is the set of all non-negative integers less than n. Non-negative, so it will start with 0 and its elements will go like this, and it can go up to m minus 1. The non-negative integers less than m, they make the set Rn. So from Rn, if you remove 0, you get the set of all positive integers less than m. Note that if m is 1, m can also be 1, that is also possible, then this set consists of what? Only one element, which is 0. In other words, R1 is the singleton set consisting of the integer 0. And in this case, this difference set is empty. And it's also a convention that when you see a list of elements like this, where the list starts from some element and then after some time it reaches some element, okay, a finite list of elements, but in some cases this last element turns out to be less than the first element. The convention is that in such a case, the list is considered to be empty, and the set it gives is also the empty set. Okay, so with that convention, this way of writing makes sense. Alright, so now we understand what we are having here. We have a positive integer m, and for that positive integer we have this set Rm. From this set, again an element A has been chosen. A is anything here but not 0. Alright, so now with these things, and you can understand what nm minus 1 is. Nm minus 1 is just this set. So with these things, we then define a function fa from Rm into Rn. What is fa? The image of any element x coming from Rn under fa is the image of ax under the remainder function. What is the remainder function? The remainder function is the function that gives us the remainder when you divide the input is some integer, by the positive integer m. You can understand why this is why we are taking this second set here as Rm. When you divide any integer by m, where m is a positive integer, by the Euclidean algorithm, these are the possible remainders. And that is why whatever remainder you are going to get for a given input, for example, say m is equal to 3, okay, and say your x is 4. 4 is some integer. We can take a negative x also and just simply taking 4. Then when you divide 4 by 3, the quotient is 1 and the remainder is 1. So that is why R of 4 is equal to 1 if our n is 3. So it is that function. And using this function, we have defined fa. Now, this is the question. For which a in this set R3 difference 0 is our function fa from R3 to R3 an injection, an injective function or one-to-one function? Let's see. Actually, there are other parts also. There are 3 more parts to this question, but let us solve each one of them. Let's first solve this and then we will go to the next. So we are going to solve them individually. Okay, so first of all, you have to write what R3 is. R3, of course, consists of 0, 1 and 2. And we are being asked which a from R3 makes that function fa an injective function. So, keeping in mind that a cannot be 0, there are only 2 possibilities. A is either 1 or 2. That means we just have to see 2 functions, f1 and f2. Okay. Because there are so few elements in R3, we can just simply calculate the functions entirely and see if they are injective. When a is equal to 1, we have f1 of, okay, so what will the inputs be? The input can be either, of course, the input is going to come from R3, so it's either 0 or 1 or 2. Keep in mind that the input can be 0, only this suffix cannot be 0. Okay, we cannot consider f0, we are considering f1, but the input can be 0. So this will be the remainder value of 1 times 0. That means the remainder of 0. Now what is our m here? M here is 3. This means that this is the remainder you would obtain if you divide 0 by 3. Since 0 itself is non-negative and less than 3, so 0 itself is the remainder. When you divide 0 by 3, the remainder you get is 0. So f1 of 0 is 0. Next, f1 of 1 is going to be r of 1 times 1. That means r of 1. Again, dividing 1 by 3, the remainder we obtain is 1 itself. And there is one more, f1 of 2, which is r of 1 times 2. When you divide 2 by 3, the remainder you get is 2 itself, because 2 is non-negative and less than 3. So what do you see here? The image of 0 is 0, the image of 1 is 1, and the image of 2 is 2. So f1 turns out to really just be the identity function on R3, which of course is injective. Hence, f1 is injective. That means for a equal to 1, the function is injective. Next, we calculate f2, because that's the other possible value a can take. First we calculate f2 of 0, which is r of 2 times 0, which is r of 0, that is just 0. Next, f2 of 1 is r of 2 times 1, which is r of 2. Keep in mind that still we are dividing by 3. So the remainder is 2. And finally, f2 of 2 is r of 2 times 2. This is r of 4. Now when you divide 4 by 3, we just saw, we just saw moments ago, the remainder is 1. So in this case, for f2, the image of 0 is 0, the image of 1 is 2, and the image of 2 is 1. This is not the identity function, but still it's a one-to-one function. Hence, f2 is also injective. That means the two possible values that A can take in both, for both those values, our functions are injective. Next, let us see part 2. For which A, this time in R4 difference 0, is if A from R4 to R4 and injection. The similar one, but now M is 4. So that means now our A can take 3 values, 1, 2 and 3. You can perhaps already see that f1 here also is going to just be the identity function, but anyway, let's do the calculation. We have f1 of 0 equal to r of 1 times 0, which is r of 0, but be careful, now the number by which we are dividing is 4, not 3. Still, the remainder is 0. f1 of 1, and also this time each function has to be calculated at 4 inputs, because R4 has 4 elements, 0, 1, 2 and 3. So when you divide 1 by 4, the remainder is 1. f1 of 2 is r of 1 times 2. Dividing 2 by 4, we get the remainder 2. And finally, f1 of 3 is r of 1 times 3. So again, the remainder is 3 itself. So yes, actually it's the identity function. So this is injective. f1 is injective or is an injection, it's up to you how you want to write the sentence. Next we calculate f2. Actually there is no need to fully calculate all the values of f2, but because we do not have any idea of how these functions actually are behaving, right now what we are trying to see is simply without having any knowledge about the functions, before we really calculate the entire function. That's why Right now let's just do the calculation, and then the calculation will tell us something here itself for F2 that we did not see before here. Okay, so what is F2 of 0? As usual, this is just R of 2 times 0, which is R of 0, and that's equal to 0. Next, F2 of 1 is R of 2 times 1, which is R of 2. Dividing 2 by 4, we get the remainder 2 itself. Next, F2 of 2, sorry. This is R of 2 times 2, which is R of 4. But dividing 4 by 4, we get the remainder 0. So, did you see that there is no need to calculate F2 of 3 anymore? That's because F2 of 0 is 0. Yeah. And F2 of 2 is also 0. So, F2 is not injective, since F2 of 0 is equal to F2 of 2, but 0 is not equal to 2. F2 is not an injection. Okay, so suddenly this is not an injective function. Next, let us see F3 also, because A can be 3 as well. Next, F3 of 0 is just 0. F3 of 1, F3 will be injective. So, what is R of 3? When we divide 3 by 4, the remainder is 3 itself. F3 of 2, R of 3 times 2, that is R of 6. Dividing 6 by 4, we get the remainder 2. And F3 of 3 will be R of 9. Dividing 9 by 4, we get the remainder 1, because 9 is 2 times 4 plus 1. So, let us now see the inputs and outputs. 0 gets mapped onto 0, 1 goes to 3, 2 goes to 2, 3 goes to 1. Okay, so this is an injection. This in fact is a permutation, it's a bijection. So, F3 is injective. Now, let us note one thing. Okay, what have we seen so far? When M is 3, in this case, the functions that are injective are F1 and F2. Both, and these are the only functions that can be thought of in this context, because our suffix a cannot be 0, and these are the only two other values available. When M is 4, F1 is injective, F2 is not injective, but f3 is injective. Do you see a pattern here? Just from these two cases, 1 and 2 are relatively prime to 3. They are co-prime. 1 and 3 are relatively prime to 4. And in those cases, the functions are injective. But 2 is not relatively prime to 4. And in that case, the function is not injective. And now the author asks a general question. Number 3. Suppose that A as usual is in Rm difference 0 and it satisfies this condition that the greatest common divisor of A and M is greater than 1. It's not equal to 1. Is Fa from, that's of course understood, from Rm to Rm, an injection. No. You can see this case. Here, this is our A, right? And this is M. And what is the GCD of 4 and 2? 2. 2 is greater than 1. And this is not an injection. But is this true in general? I mean, this is only a special case. Is this true in general? Is it always the case that if such is the case, that if this is our beginning point, then Fa is not an injection? Yes, it's true. And one more thing, how did we get the fact that this is not an injection? Note that F2 of 0 was 0 and something else also became 0, that is F2 of 2. So we are going to use this observation somehow to answer this general one. The goal is to somehow create M here or a multiple of M. For example, here we created a multiple of 4 itself. So when you calculate its remainder function value, you get 0. And of course, we are going to use this condition. Let D be the GCD of A and M. Okay. Now, what is given? It's given that D is greater than 1, right? Since D is greater than 1, so M divided by D is less than M. Do you see what type of number M divided by D is? Because D is the GCD of A and M, D after all divides M as well. D divides A, D divides M, D divides both of them because it's a common divisor. It's the greatest of all common divisors. That thing is also there, but after all it's a common divisor, so it divides M in particular. That means this is an integer and a positive integer, of course, because D by definition being GCD is positive and M was already positive from the beginning. So this is the positive integer and it is less than M. Why? Because D is greater than 1. If you cannot immediately see how this is true, Just take reciprocal on both sides. That will give you what? Less than 1. When you take reciprocals of both sides of an inequality where the numbers involved have the same sign, either both of them are positive or both of them are negative, the inequality changes direction. And then you can multiply both sides of this by m, and this time, however, the inequality won't change direction because m is positive, and that's how you get this. All right. So m over d is a positive integer less than m, and that makes m over d an element in Rm, isn't it? Because Rm is the set of all non-negative integers less than m. A positive integer also, of course, is a non-negative integer, and it's less than m, so it belongs to Rn. Now, what will happen if we calculate fa of m divided by d? This will be the remainder function value of a times m over d. Now this can be rearranged and written like this. Okay. Now the thing is that just like d divides m, because of which m over d is an integer, d also divides a. So a over d is also an integer. So that means here we are looking at an integer multiple of m, but remainder function with respect to what? We are dividing by m, right? So if we divide a multiple of m by m, the remainder we will get is 0. However, something else is also 0, which is r of a times 0 or fa of 0. Does this tell us that fa is not injective? Yes. How? Because the inputs are different, although the outputs are the same. M over d is not 0, it's a positive integer. Since this is not equal to 0, in fact greater than 0, fa is not an injection. And then the final part. What happens if the GCD is really equal to 1? Do we then always get an injection? Yes, this time we will always get an injection. So I just simply have to change this. Is this now an injection? Yes, it is, and we have to prove it. What did we have? I think, suppose that, nothing important. Okay, so now in this situation, we have to prove that our FA is an injection. Let's see what we can do. So we are going to do this, of course. See, there are obviously two ways of proving that a function is an injection, and they are logically equivalent. Either you take distinct inputs and show that the outputs are also distinct, then the function is injective, or you take two equal outputs and show that the inputs are also equal, then also the function is injective. These two things are contra positives of each other. Each one is an implication after all. So we are going to use that second one. We will assume that for any two inputs, their outputs are equal, and then we will try to prove that the inputs are also equal. So let x and y be two elements in Rn such that fa of x is equal to fa of y. Now we want to prove that x is equal to y, but we can assume without loss of generality that x is less than or equal to y. I mean, one of them will be less than or equal to the other. Without loss of generality or without losing generality, that x is less than or equal to y. But let us also note what other inequalities these numbers are going to satisfy. They belong to Rm, right? And what type of numbers does Rm have? Rm consists of all non-negative integers less than n or less than or equal to m minus 1. That means our x and y are also going to satisfy this. Okay. Now let's see what we can say from here. But before we do so, let us also see, because if you just simply write what fa of x is, it's the remainder function value of ax. Now that remainder value is equal to the remainder function value of ay. However, when we divide ax by m, this is the remainder, but we don't really know what the quotient is. So let's just assume that the quotient is something. We have from the Euclidean algorithm that ax is equal to, say, q1m plus r of ax. This, by the definition of the remainder function, is the remainder, and quotient is, say, q1, and ay similarly is some integer times m plus the remainder value of ay for some integers q1 and q2. Okay. Now it is given that these two things are equal, right? Fa of x is equal to fa of y. So this implies what? R of ax is equal to R of ay. But now we can use these two equations and write something here in place of R of ax, namely ax minus q1 of m. Similarly, R of ay is ay minus q2 of m. Okay. Now we have assumed that y is at least x. So let me just rearrange things, and I am going to get this q2m minus q1m is equal to ay minus ax. q2 minus q1 times m is equal to a times y minus x. All right. So from this equation, what do we see? Because q2 and q1 are after all some integers, this is an integer multiple of m, the left hand side. So the left hand side is divisible by m. That means the right hand side is also divisible by m. So this last equation further implies that m divides a times y minus x. Now since the GCD of m and a is equal to 1 because they are relatively prime, so by Euclid's lemma there is a result. I am not exactly sure if this result has already appeared in this book, but it's a well-known result that when you have a divisibility relation like this, and in terms of division, m has nothing to do with a. This is a very vague way of saying that m and a are relatively prime. Or another more easily understandable way of expressing this is that if you have like this now, there is no cancellation that goes on between m and a, no common factor other than 1. 1 is the greatest common factor. And that is why from the above divisibility relation we have this. Now let us see what type of number y minus x is. From this inequality, we immediately see that y minus x is non-negative. In fact, I can start from here itself. Since I don't know what is happening today, everything is falling in place so nicely. Since we have this, so y minus x is non-negative because you can subtract x from both sides of this middle inequality. Here you will get 0 and on this side you will get y minus x. But this is also less than or equal to y. Why? Because x is non-negative. If x is 0, y minus x is simply y. Otherwise x is positive. So you are subtracting something positive from y. In that case it will get reduced. Okay, so it is in general either equal to y or less than y. But y is less than or equal to m minus 1 and m minus 1 of course is less than m. Now you concentrate on these three numbers, y minus x, m and 0. M is a positive integer, y minus x is a non-negative integer, and we are also saying that m divides y minus x. If y minus x is positive and less than m, is it possible for m to divide y minus x? No. For example, 4 never divides 3. 3 is positive and less than 4. You will get a contradiction if you forcefully suppose that 4 divides 3. In fact, I urge you to see why. Okay, using the Euclidean algorithm, you can create a contradiction very easily. And that is why y minus x cannot be positive. But keeping this thing in mind that y minus x has to be non-negative, This means that y minus x has to be equal to 0 because it cannot be positive. The only other option for it to be is that it is 0. But then y minus x has to be equal to 0, i.e. x has to be equal to y. This is what we wanted to show, right? We assume that the FA images of x and y are equal, the outputs are equal, and now we have successfully shown that the inputs are also equal. Hence, FA is injective or is an injection. The next exercise that there is after this in the text asks the similar question, but where the word injective or injection is replaced with surjection. All these things, are these functions surjective? In both those cases, is the function FA surjective? I am not going to do that. Okay, I ask you to do that, and if you do not get, or if you find it very difficult, you write in the comment section below. Okay, then we can discuss it. So that's just it for tonight. Tomorrow we do not have any upload. Day after tomorrow, of course, we again have our usual calculus upload. So see you with that day after tomorrow. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.